Okay. It's my pleasure to introduce Haille Perkins, who is a second-year graduate student in the Department of Astronomy. She did her undergraduate research at St. Lawrence University in upstate New York. She's such a powerful force of science that she needs two advisors, both Gautam Narayan, who happens to be the deputy director of CAPS, and Brian Fields, the former chair of astronomy. She's working and will be telling us about binary neutron star mergers and kilonova. This will be a 30-minute slot, and then we'll transition over to Yuji after this, okay? Let's give Haille a warm welcome.
Hi, everybody. I'm going to talk about looking for binary neutron star mergers and surveys, because this is CAPS. And so, to understand why I care about these binary neutron star mergers, I have to give you this introduction to nucleosynthesis. And so, we know that the Big Bang, cosmology tells us that hydrogen and helium came from the beginning of time. However, everything heavier than that has come from the death of massive stars. And so, I won't go into the science of supernovae, but you know that the stuff in the green and the blue come from core-collapsed supernovae and type 1a supernovae. And so what I'm more interested in is the stuff in the yellow and the orange. And so this comes from when a heavy nucleus captures a bunch of neutrons, and depending at the rate at which that happens, you get the yellow or the orange. And so the yellow is for slow capture, or the slow process, S process, in which the neutron is captured so slowly that the neutron has enough time to beta decay and become a proton, and that nucleus slowly moves down the periodic table. But in the case of the rapid or R process, the nucleus is bombarded so rapidly it does not have time to decay. And so it gets all of these neutrons, and eventually it's not bombarded anymore and has time to decay. And when that comes, it has so many neutrons, they all turn into a lot of protons, and then it ends towards this bottom portion here in the orange. And what's really interesting about those is these don't pertain to us biologically, but they have a lot of cultural relevance to humans, such as gold and silver and uranium. And the only place in the universe we think that might happen is binary neutron star mergers. Enough stuff that has enough neutrons to capture them rapidly. And so there's only one case where we think this has happened, a confirmed binary neutron star merger in 2017. And it was accompanied with its transient, the kilonova, which is the decay of all of those heavy elements. It's powered by the decay of those heavy elements, much like supernovae are powered by the decay of cobalt and nickel. But the reason we were able to find this is through its gravitational wave detection. And this gravitational wave detection allowed us to construct this localization map in 3 dimensions as well. This is only 2 on the sky. But through this localization, people went on a multi-wavelength campaign to search for this transient you see here. And so that was found about 11 hours after the merger, thanks to Coulter et al. It was found in NGC 4993. And so, compiling all the observations, Viller et al. Did some modeling. This modeling, you can only get this kind of light curve if you have those R process elements. So that's why it makes them quite interesting. However, do we think gravitational waves will let us find the next one? So here is a schedule of LIGO-Virgo-KAGRA gravitational wave network. So on the bottom is time, and the little colored bands indicate when we are looking for gravitational waves. And GW 170817 was back in 02, approximately 3 days after Virgo turned on. But we are now up to 04, we're in the second half of it, in 04b, and we only have about 10 months left. It's scheduled to end about the February of 2025, which is unfortunate, because that's when LSST is supposed to turn on, if all goes well. And so therefore there's no overlap between the gravitational wave detections and when LSST is going to be scanning gigantic portions of the sky to look for these transients. Also, I'd like to graduate, so I need to find these things before so I can do some science. So this is unfortunate timing. And so ignoring the downtimes, quantitatively, how bad is it? Fortunately, there's me. I helped Vade, an undergrad who's now going off to Northwestern, assess how many gravitational wave events will be followed up with observable kilonovae. They're quite faint, so it's kind of hard to see them. And it turns out, with current sensitivities and the expected brightnesses of kilonovae, we only expect 0 to 5. And it's looking more like 0 as we only have 10 months left, and Virgo got a mirror damaged, and KAGRA, I think, was hit by an earthquake. So they're out of commission for a while, and we only have 2 of these detectors. And so looking out further, pretend I care about O5, even though I'm going to graduate, there's an order of magnitude improvement, which is great for the people who will be around. Maybe it'll be great for me in my postdoc, but not for me in my thesis. So what else can we look for? And so, as I said, there's kilonovae, and they're powered by the decay of all of the heavy elements that are synthesized in the blast, but they're very, very faint compared to supernovae. They're like 1,000 times rare and even 1,000 times dimmer. So they're hard to find. But binary neutron star mergers also produce gamma ray bursts, which is a very narrow, not isotropic at all, beamed emission of high energy gamma rays. And while I don't care about the gamma rays, because it's not in the optical range of LSST, what it does to the ISM around the merger is quite interesting. The GRB slams into the ISM, shocking it, and produces synchrotron, which is observable across the electromagnetic spectrum, and it can be quite bright in the UV optical IR. And so to give you context on how bright it can be, here's a model of GW170817 in the U and I band, and I've taken what the kilonova looks like and what the afterglow looks like. You don't see a difference between these 2 bands because we observe the afterglow not on axis. So where the GRB shocked the ISM, we were not looking at that direction, so we did not see the light until that shock moved out and crossed our line of sight. However, if we were to have been observing it on axis, we see a very large enhancement, about 6 mags. 5 magnitudes is like 1,000 in flux. So we have a lot larger window to search for these events, which means my CAPS work is building a model that combines both of these emission and then plugging that into Antares to search for these kinds of things. And so I made a little schematic here of what I've done. To do this, my modeling involves combining spectral energy distributions, or in this 3-dimensional space, you choose a time and a wavelength, and it provides you with the flux expected from such an event. And so here's the kilonova. Don't really look at the details there. That part doesn't really matter. But by the simple power of addition, I slap an afterglow on top, and then we get the combined result. And so that part's pretty simple to understand. What's more complex is the actual physics related to these events. And so for kilonovae, a typical way to model these things is via grids, or like SEDs that have only been sampled for a very small parameter space. And the way that they have generated these is through lots of complex radiative transfer, but the physical model is as such. And so we're looking at, so the 2 objects merge, we can look at the edge of the disk, and that's what we're seeing here. So this is the plane of the disk, the orbital plane. And this is in velocity space, but you can pretend it's position, because the stuff that's moving faster will get out farther. But when these things merge, they throw out 2 different types of ejecta. So they merge and they throw out stuff in all directions, and that's referred to as the dynamical ejecta. And based on, I think, neutrino radiation and some other things, the R process, or like the heavy stuff, is concentrated to the disk, and that's what this like red region is the heavy or lanthanide fraction. And so also some of the material can fall and form a disk around the compact object, and that will throw out some additional material. And so to model kilonovae, you need to know how much material is thrown out, what range encompasses the heavy stuff, and where we happen to be looking at it. Because if you look over here, you're looking at a lot of heavy things, it's very opaque, whereas up here it's a little bit lighter, so the transient can look different. So, moving on, back to what they'd worked on. So, to do the analysis that was counting how many kilonovae we would observe, he had to be able to generate a wide range of kilonovae. We just had some grids, which are a finite sampling of what they can look like, and so he built an interpolator, which I used in my model, such that you give it whatever parameters you're interested in, and then you can get an SED, and then you take S and Cosmo, tell it what band you're interested in, along with maybe some information if you care about extinction and whatnot, and then you can get the light curve that you so wish for. But moving on to afterglows, so I want to take my kilonova and then slap an afterglow on top. I use a Python package called afterglow. Instead of requiring interpolation, I just give it the parameters and the time and wavelength of interest, and it can give me the flux density that I care about. So I use this to create my afterglow SEDs. And these are parameterized by this list of things over here, and I hope this physical picture can give you an idea of why those things matter. So we're looking at it, I guess, from the side. The merger happens over there, it throws out all the ejecta, and then the gamma reverse comes out and zaps the ISM, producing all these pretty colors. And so from this, I think it makes sense that the brightness of this synchrotron would depend on how much energy went into the blast, how much material it is slamming into, where we are looking at relative to where the ISM was shocked, and maybe the distribution of how narrow that jet is of the GRB. It's very highly collimated. So I just stole from Vade. I have an SED. He did all the work to make them into light curves, so I just shove afterglow pi in the middle. And so now I take my afterglow pi, I add my kilonova in there, boom, I get the light curve. So now that I can make a light curve of whatever kilonova afterglow combination I wish, I actually want to know what things can we observe. And so, as I said, all these things, both of these components depend on a range of different things, and so that means they can look like there's a wide range of possibilities in the light curves. And so I will thank Brian for this analogy, but it's kind of like dogs. So the underlying genetics means that dogs will look a little different. You can have like long furry hair, or you can have a short snout, or there's a lot of different colors, and maybe they're running and excited about the life, but it's kind of like our kilonova and afterglows. You can imagine that as a result, the next one probably won't really look like the one that we saw. We can't expect that the neutron stars involved will be the exact same mass. We can't expect that the composition will turn out exactly the same. And especially in the case of the afterglows, which it turns out that GW170817 was underluminous relative to other GRBs. And so we can expect that maybe in that regard it might be brighter, or that it's in a different environment, or we only saw it from one direction, so it's very likely that we're not going to see it from the same viewing angle. And so going back to my little model, I took a kilonova, slapped an afterglow on top, and I get this combined SED. But before I do that, I need to sample reasonable parameter distributions such that I can get light curves that accurately model what we might actually observe in LSST and DTF. And so scoured the literature for that, mostly Fong et al. For the afterglows, and parameter distributions about how neutron stars are born and recycled to get the parameters at which we could observe kilonovae. And so here's my predictions for LSST. What I've done here is I take all that work that I just did and repeat it 5,000 times. So I pick 5,000 parameters, plug it into my kilonova model made by Vade, and so I get, this is the kilonova, so I take 5,000 of those, this is the median light curve, and then this is the 16th and 84th percentile, so kind of to say that of those 5,000, most of them lie in this like orange region. But you can see here that it peaks at like one day, very, very short, and it drops off many, many, many magnitudes in just a couple of days. However, if you add on top of that the afterglow, you see that there's a pretty big gap there. And so these are viewed slightly off axis, so it's not entirely random which way I was looking at them, but like 30 degrees off axis, so you can still see the afterglow and the timescales of interest. But in this case, if we look at about 10 days, we see that for the sensitivity of U-band of LSST, if we were just looking at the kilonova, it would only be observable out to 500 kiloparsecs. If the afterglow shows up, and we can see that, we can extend it out to 20 megaparsecs, which is a factor of 40 in distance, otherwise a factor of 64,000 in volume. I'd also like to note that I have selected U and G band here. So in the case of kilonovae, we expect them to be fairly red because there's a lot of heavy elements involved, and so relative to, when comparing the kilonova and the afterglow, we expect a much larger enhancement in the U band. And so I'm just showing that here. It's quite much larger in this bluer band than it is this more towards the optical. And so since we saw that it was so much brighter in the U band, let's look into the future of what can we see if we look the next generation of ultraviolet telescopes. And so just recently, NASA picked their mission. There was 2 competing, StarX and UVEX, and they decided on UVEX, which is preferable to me because StarX is more for X-ray. But we will see out to 26 mags, and it's designed for following up gravitational waves. By the time it launches, that will be more relevant, but this is just predictive. And so here we see an even larger discrepancy. And so this is the farther UV, and this is the near UV, but again, because it's in the bluer side, we see a much larger enhancement between the expected kilonova and slapping on top an afterglow. And so all this is to say that the UV is a pretty good place to look for binary neutron star mergers. So if you see something that has like a few points and the kilonova fades, and you're like, oh, maybe that was a kilonova. You can follow it up later in the UV and confirm if you see the afterglow and be like, oh, maybe that really was a binary neutron star merger. And because there is this large enhancement, both like vertically, we see that it's brighter, so that means we can see it up farther, but also in this, you can also think about it in the other way, we have more time because it is brighter longer. And so, while in this case, we're not really going to see them on axis, or directly on axis, so most of the time you're going to see the kilonova for a little bit, and then the afterglow. And so we don't get a lot of information about the kilonova, but if we find these things, we can go back and look at the hosts and understand where these systems come from, and then maybe, if you catch it early enough, do some spectroscopy to find these are process elements. But what I have left to do is find a rate at which these things are expected to show up. We know roughly how many binary neutron star mergers occur, and since this afterglow enhancement depends on the angle at which we observe them, I'm going to figure out how often we can expect to see this enhancement. And then make an Antares filter so we can start checking ZTF and then maybe LSST for these things. And then after I am done all that, which will conclude my CAPS work for this time, I will work on my thesis, which will hopefully be studying more weird transients like kilonova or maybe something else entirely different. And so I would like to thank CAPS for funding me to do this. So, thanks everybody.
Questions for Haille?
Thank you for the great talk. I'm curious what other types of transients would be most likely to be like a contaminant in a kilonova sample?
I can't remember. So if you are in the IR, there's a lot of stuff in the infrared, whereas in the UV, there isn't a lot of other transients. I can't say which ones actually show up there, but I suspect that's where people are looking for like shock breakout and supernovae, so maybe something like that. But I don't know off the top of my head what specific contaminants are.
Thank you for the talk. Can you go back to the previous slide about the UVEX? Yes, like that. For the far UV, for the like kilonova only curve, why is there like multiple bumps after a long time?
I spent a lot of time on this. Thank you. So I'll kind of go. What I think is happening here is a difference in opacity, and so the kilonova, if you're looking at it. So in the case you're looking at, it was like mostly on axis. With regards to the kilonova, it means you're mostly looking at this part. So this material is going to emit bluer, it's lighter, it's not as opaque. And then slightly later, you'll see the disk wind. So I think the first part is the dynamical ejecta doing the most you can, and then the second part is the disk wind showing back up. That is my physical intuition of why it has that second bump. And you only see that in the UV because these are, in the IR, it's blocked out by the heavy stuff. Or like in the optical, it's like that blue emission is blocked out.
Thank you.
What sort of host studies are possible or are you interested in?
Well, we haven't seen many of them. So, what I think can be done is in the same way Alex Galeano did with supernovae, such that at early times, if you know the host information before you see most of the light curve, you might be able to predict or use like classification to figure out, oh, maybe that is going to be a kilonova instead of something else. And so he was able to pick out different types of supernovae based on knowing what the host information is. So maybe something like that.
Any other questions?